Welcome back. In this section, we're going to discuss some functional thinking in elementary students in grades 3 through 5. So we're going to take a look at how growing patterns develop this functional thinking. Patterns are found in all areas of mathematics. Learning to look for patterns and how to describe, translate, and extend them is part of thinking algebraically. 2 of the 8 mathematical practices actually begin with the phrase "look for," implying that students who are mathematically proficient pay attention to patterns as they do mathematics. Identifying and extending patterns is an important part of the process in algebraic thinking. By 3rd grade, students will have had numerous experiences with repeating patterns that have a core that repeats. In addition to simply extending the patterns using materials or drawings, they should also have translated patterns from one medium to another. For example, a pattern made with triangles and circles can be translated to one involving red and yellow circular counters. The essence of both patterns remains the same. When two patterns made with very different materials are each read in the same manner, how they are mathematically alike becomes obvious. They have the same pattern structure. Students typically use materials such as color tiles, pattern blocks, toothpicks, or simply drawings to both copy and extend patterns that repeat. A few examples of repeating patterns are shown here. The study of patterns and functions is infused throughout most standards and explicitly addressed in these particular standards. So in grade 3, you have the students identifying arithmetic patterns. These may include patterns in the hundreds chart or multiplication tables. Then in grade 4, they generate a number or shape pattern that follows any given rule, identifying apparent features of the pattern that were not explicit in the rule itself. And then in grade 5, they generate 2 numerical patterns using 2 given rules, identifying apparent relationships between the corresponding terms. For most repeating patterns, the elements of the patterns can be numbered 1, 2, 3. This is what we call the terms or the steps. This activity requires consideration of these terms and is a forerunner to looking at the function aspect of patterns. Take a second and press pause to consider. Read through this, consider it, play around with it, and then press play when you're ready to continue. Students are surrounded by patterns in the world around them, and these patterns can be analyzed or used to make predictions. One context is the Olympics, the Summer Olympics that were held in 2020, 2024, and then every 4 years. The Winter Olympics held in 18 and 22, and so on. So you could ask students to create a way to determine if X year will be an Olympic year, a Summer Olympic year, or a Winter Olympic year. Hurricanes are also named in a repeating manner and can be analyzed and generalized, and that's what this activity shows. So pause and read through this and then press play when you're ready. Students can explore patterns that involve a progression from step to step or term to term. In technical terms, these are called sequences. We will simply call them growing patterns. With these patterns, students not only extend or identify the core, but also look for a generalization or an algebraic relationship that will tell them what the pattern will be in any point along the way, so like the nth term. So this picture is a growing pattern in which step 1 requires 3 triangles. Step 2 requires 6 triangles, and so on, so that we can say that the number of triangles needed in a function of which numbered step it is. So like if we wanted to know the 9th step or the 15th or the nth step. Geometric patterns make good examples because the pattern is easy to see and students can manipulate the objects. This picture illustrates 4 different growing patterns though the possibilities of the visuals are endless. The questions in this activity can be mapped to the triangle pattern and can be adopted to any growing pattern. and help students begin to reason about functional situations. Analyzing growing patterns should include the developmental progression of reasoning by looking at the visuals, then reasoning about the numerical relationships, and then extending it to a larger or nth case. Students' experiences with growing patterns should start with fairly straightforward patterns, such as in this one right here, and continue with patterns that are more complicated. So press pause, read through this, and think through it. So a more complicated pattern might be this dot pattern. When discussing a pattern, students should determine how each step in the pattern differs from the preceding step and how to operate on the value of the current step to get the next step. Examples should encourage students to use both additive and multiplicative strategies. Growing patterns also have a numeric component, the number of objects in each step. One row of the table or chart is always the number of steps, and the other is for recording how many objects are in that step. Analyzing growing patterns should include the developmental progression of reasoning by looking at the visuals, then reading about the numerical relationship, and then extending to the larger or nth case, as I said previously. Students' experiences with growing patterns should start with fairly straightforward patterns in grades 3, such as the one we saw before, and continue with patterns that are somewhat more complicated, as they are asked in grades 4 and 5 to generate and analyze patterns. With the shift to the heavy focus on fractions in grades 3 through 5, including fractions and decimals in working with growing patterns is a crucial algebraic connection to foster. When looking for relationships, some students will focus on the table and others will focus on the physical pattern. It is important for students to be able to use both representations. If a relationship is found in a table, challenge students to see how that plays out in the physical model and vice versa. The patterns discussed so far, repeating and growing patterns, are far from the only patterns in mathematics, not even all the options in the growing patterns. Students not only need opportunities to explore patterns, but also to learn to expect, see, and use patterns in all of mathematics. If you want to go to a website called visualpatterns.org, you will see hundreds of different visual patterns that you could use for your classroom. Functions are relationships that describe situations that demonstrate joint variation or covariance. Although functions and function notation is the focus in 8th grade, experiences with functional thinking situations must begin with meaning-making experiences in the elementary grades. First, geometric growing patterns provide a concrete and engaging way to introduce functions. Second, context builds meaning for functions and for the relevance of algebra in general. Third, thinking of functions in an input-output manner helps students develop the meaning of function. Algebraic thinking also involves learning different ways to represent functions, as we saw with growing patterns. Functional relationships can be represented in real context, in a chart or table with a graph, with an equation, and with words. Each different representation offers a different way to think about relationships and thus helps us better understand them. Notice the explicit connection in this story to the input-output concept of patterns and relationship. Something goes in the pot, and then something came out of the pot. When students examine real-world functions or explore growing patterns, the relationship is found in the context. For example, horses in a race. Students should be engaged in conversations in which they think the multiplicative relationship to the context, such as for every one horse in the race, there are 4 legs. Another student may say 6 legs for every horse if you are counting the jockey. The student's task is to represent relationships in a variety of ways, including words, pictures, numbers, charts, and graphs, and equations. Another important type of activity is to determine the relationship or the rule by simply observing the numbers that are paired up without a context involved. This could be done by giving students a partially filled in chart and asking them to determine the rule. So press pause to consider this activity and then press play when you're ready to continue. A completely equivalent format that is generally more fun is a function machine, as described in this activity. So press pause, read through this, and then press play when you're ready to continue. Here's another one. I personally have used the yellow hexagon pattern with classes of teachers for years. There is so much to explore algebraically. So press pause and then press play when you're ready to continue. So far, patterns have been represented by, first, physical materials and drawings, second, tables, third, words, fourth, symbols. A graph adds a fifth representation. In most standards, coordinate graphs are introduced in 5th grade, in which students represent real-world data and solve mathematical problems in that first quadrant. This figure provides a graph of the border tiles problem and shows a graph for the dot pattern. Here are some of the examples of real-world situations that give rise to graphs for intermediate grade students. These real-world examples provide opportunities to connect the graphing points on the coordinate axis with algebra. Ask questions about what students notice about their data on the graph. What might they predict for an x value they did not plot on the graph? Why? How does the graph provide insights into the situation? Try this with 5th graders who are exploring the volume of solids. Consider this task of a tower creating 1-inch cubes. The base of the tower is 2 inches by 3 inches. As the height of the tower changes from 1 inch to 10 inches, the volume of the tower will increase in 6 cubic inch increments for each inch added. The equation would be the volume equals the height times 6, and the graph will be a series of points that are in a straight line. The graph or the equation can be used to predict how many cubes would be needed for a tower of any height, or if the number of cubes is known, to be able to build or to be able to determine how tall of a tower could be built. See you later.